All right, so in this video, I'm going to wrap up 1.3, and there's a section towards the end that asks you to, figure out the functions even or odd. And in the past, this topic was not introduced until math analysis, but you've probably seen this topic at some point in Math 3 or even Math 2. Okay, but if you haven't, here is here are the notes. Okay, so let's take a look at a function you guys are familiar with, right? F of x is equal to x squared. And a function like this, right, you can see that it's symmetric to the y-axis. And so this is actually called an even function. Okay, so this is an even function. And what are some characteristics of an even function? Well, one, you know that it's symmetric to the y-axis. Okay, symmetric to the y-axis, right? You can inspect that it's symmetric to the y-axis, okay? What's another thing that's true? Well, if I take x comma y, right? X comma y, if I reflect it across the y-axis, right, it has an equal distance to the y-axis, right? It's actually negative x comma y, okay? So that's coordinate notation, right? X comma y becomes negative x comma y, and vice versa, okay? All right, symmetric to the y-axis, x comma y becomes negative x comma y. And if we were to use function notation, right, let's say I call this x comma f of x, right? And I'm going to call this guy right here negative x comma f of negative x, right, using function notation. Well, what do you observe? You can see that this y value and this y value are the same. So you can say f of negative x, right, is just equal to f of x itself. Okay, so three things are true of even functions. They're symmetric to the y-axis. X comma y becomes negative xy. And f of negative x is equal to f of x, right, because these two y values are basically the same. All right, so that's true of all even functions. And I use the simple example of a parabola. All right, well, what about this next function right here? We'll call it f of x is equal to x cubed. Okay, f of x is equal to x cubed. Okay, so roughly, f of x is equal to x cubed is going to look something like this. Okay, I'm not going to draw the tick marks, but this is f of x is equal to x cubed. All right, so what can you observe from this? Maybe let's plug in a point, okay? We'll call it 2, 8, and down here we'll call this guy negative 2. If you plug in negative 2 in this function, you're going to get negative 8. Okay, so what can you observe in general, right? This is x comma y. And by the way, right, this is actually called an odd function. Okay? Odd function. So first things first, before we actually get into the coordinates, an odd function is symmetric, okay? It's symmetric to the origin. Symmetric, not to the x-axis, but it's actually symmetric to the origin. And what that means is it's symmetric to the y and the x-axis, okay? And so, if I may show you here on the side, right? If I take this part of the graph right here and I reflect it across, it doesn't matter which order you go, okay? If I reflect it across the y, right? And then I take this portion and reflect it across the x, that's where I end up. So that's what it means by symmetric to the origin. It's symmetric to both y and x-axis. And I showed you here on the side what that means, okay? You can go over x and then go over y. You still end up in quadrant number 4. All right, so first things first, all odd functions are symmetric to the origin, which means it's symmetric to the y and x-axis. What about the coordinates that I wrote over here? Well, x comma y, right, becomes negative x comma negative y. So x comma y becomes negative x, negative y. All right, and then what about function notation? So instead of using x and y, let's say I call this guy x comma f of x. Okay, actually let's just call this x comma f of x. And then we'll just call this point x comma f of x. And then we'll call this point right here negative x f of negative x. All right, so we'll say negative 2, negative 8 is negative x f of negative x. Well, unlike the previous example, right, I can't say that this y value and this y value is the same, right? I can't say that negative 8 is equal to 8, right? What I can say, though, is that negative 8 is equal to the negative of 8, right? And so using function notation, I can say f of negative x is equal to the negative of f of x, right? These two are equivalent statements. Over here, I had some coordinates. Over here, I just used function notation, okay? So algebraically, what's true? If I plug in a negative x, it's equal to the negative of f of x. Okay, so that's true of all odd functions. They're symmetric to the origin. Xy becomes negative x, negative y. F of negative x is equal to the negative f of x. And you can observe that from the graph. Okay. All right, so at this point, you're like, okay, we have symmetric to the, y-axis. We have, for even functions, we have symmetric to the x and y-axis, which means it's symmetric to the origin. What about symmetry to the x-axis? This is more of an FYI. If I were to draw you a graph that is symmetric to the x-axis, it would look like this. And immediately, okay, by the way, this equation, I'm going to call it an equation, x is equal to y squared. If you learn conics, this is a sideways parabola, okay? The y is being squared here. Immediately, you can tell, right, that it's symmetric to the x-axis. But here's the thing, right? This is clearly going to fail the VLT, right? A single x is going to have multiple y's, right? X comma y, x comma negative y already fails the vertical line test, right? So first of all, anything that's symmetric to the x-axis is not a function, right? You can graphically see it's going to fail the VLT, and of course it does not meet the definition of a function. So you don't really have to worry about anything that's symmetric to the x-axis, but just realize it's not a function, okay? And of course, if you're curious, right, x comma y becomes x comma negative y. Just wanted to show you that anything symmetric to the x-axis is not a function, okay? And you can see for yourself, right, it's going to fail the VLT.